Let's get started. Today we'll be talking about boosting, and at the end of lecture we'll touch on another method called ensemble selection. Today we'll sort of start by looking at a high-level overview of ensemble methods. Actually, bagging, which we saw the previous lecture, is also an instance of an ensemble method, but we'll sort of try to look at it from a broader perspective, and then from that segue into boosting, and finally ensemble selection. So again, let's talk about the true distribution. This is sort of one of the key themes and the bias variance trade-off that will sort of govern also the discussion on boosting. So we have this true distribution of data. We collect data, a training set sampled IID from this true distribution. We train a model on this finite training set. And then, our goal is to, at least conceptually, minimize this test error on this true distribution from this model that we train on our finite training set. And overfitting happens when the test error is much higher than training error. So, this is sort of a pictorial view of what's going on, where we have this true distribution from which we collect a finite training set, and then we train a model. And the test error, of course, is on all of these guys, which we don't get to observe. And the way we think about the test, test error, one way relative to a training set of a certain size is to treat the training set itself as a random variable, which in the thought experiment would be, suppose we could have repeated this process over and over again, collect the training set, training a model, and so on and so forth. Then the classifier or the model or the predictor that we train is also a random variable. It's a random function. Whose randomness is defined by the randomness of the training set collection process. And now we can talk about the expected test error of a function class, which is over the randomness of the training set collection, what is the expected error of the model that we get on the true test distribution. So that's what this last equation is saying. And the reason why we care about this, or one of the reasons why we care about this, is the bias variance decomposition. So for squared error, the expected test error decomposes very cleanly into a variance term and a bias term. And you get this decomposition in this sort of 1D regression example for linear, quadratic, and cubic function classes. And so some models or model classes have high test error due to high bias because the model class is too simple. Even if you have infinite training data, you can't make accurate predictions. And some model classes have high test error due to high variance because the model class is unstable, because with the amount of training data you have, if you were to repeat this process, it would give you a completely different model because the model class is too unstable with the amount of training data that you've provided it. So the concept of ensemble methods is to combine multiple learning algorithms or multiple models or model classes in a way that can better balance this bias variance trade-off. And so in the previous lecture, we looked at bagging and random forests, and today we'll look at boosting and ensemble selection. You could think of this as a sort of meta-learning approach. We're not really innovating on the baseline or core learning algorithm, so we're not proposing a new SVM or a new decision tree or anything like that. We are looking at a meta approach that uses any core learning algorithm or core model class as a subroutine, and then we do something with it. So in bagging, what we're doing is we're writing basically a for loop around a core learning algorithm, like a decision tree learning algorithm, where the for loop bootstraps new training sets, trains a model, and then finally combines all the predictions by some sort of aggregation process. So that's what a quote-unquote meta-learning approach is doing. So one of the ways we can think about why ensemble methods work well in practice is through the lens of the bias variance trade-off. Bagging reduces the variance of low bias models, right? So these really complex, minimally regularized decision trees are high variance, low bias models. They're complex and therefore unstable. And so bagging averages a bunch of them together to create more stability. Boosting, which we'll talk about today, reduces the bias of low variance models. Low variance models are typically very simple and have high bias. The simplest being a decision tree of size 1 with one internal node. So it splits on a single feature just once. Boosting trains a sequence of these simple models and combines them in a way such that the aggregate prediction looks more complex. So now we're going to talk about boosting, which is going to be the bulk of the lecture. So some terminology. We'll be using shallow decision trees for the bulk of this lecture. A shallow decision tree is simply a decision tree with a few nodes. So these have very high bias and very low variance. Different training sets sampled from the same distribution tends to lead to very similar decision trees. In the extreme case, with exactly one split, so this guy right here, that's called a decision stump. Oftentimes, these models barely have better accuracy than a static baseline, just a bias term. If you just predict the majority class, for example. Oftentimes, these methods are barely outperforming that. The reason why we're going to use shallow trees or decision stumps in this lecture is because they tend to learn more or less the same model if you were to repeat the data collection process, right? So in other words, they have low variance. So if we collect this data set and we'll learn the decision stump, it might look like that. Collect a different data set from the same distribution, learn the decision stump, it might look like that, and so on and so forth. So these are examples of decision stumps trained on different collections of training sets, sampled from the same distribution, and you see more or less the same model. A decision stump trainer is known as a weak learner. So a weak classifier is a classifier that has an error rate that's slightly better than random guessing. And here I'm going to assume that classes are balanced for simplicity. And a weak learner is simply a learning algorithm that can learn a weak classifier. And that's what decision stumps are. Okay, so the idea of boosting is that we're going to figure out a way to boost these weak models so that the aggregate of this boosting process yields a complex model. So recall this is the bias variance trade-off for squared error. So we assume that our function class has high bias and low variance. The opposite of the previous lecture when we looked at bagging. So bagging won't work, right? Bagging only reduces the variance and doesn't really touch the bias. And so bagging on a set of weak models will not do anything. So here's a first try for one-dimensional regression. So we're going to learn a decision stump, which is just a decision tree with a single split, and we're doing regression. So we're predicting a real value number. And it's a single dimension, so this function is basically y equals x squared. So the target is basically the square of our single dimensional input feature. So this is our training set right here, xy pairs. And this is the optimal split of this single feature. So everything over here, we predict the mean of the y's. And everything down here, we predict the mean of the y's over here. Okay, so now we're going to create a modified version of this training set where the new y's, I'll call them y2, is simply the residual. So what's left over? So basically, this is supposed to be 0. We predicted 6, so the residual is minus 6. This is supposed to be 1. We predicted 6, so the residual is minus 5. So on and so forth. And now we're going to create a classifier that maps x, the original x, to y2. And we're going to train a single decision stump, so a single split on this feature, on this y2. So the training set is x comma y2. And so this is the best split, and this is the prediction of the two leaf nodes. The aggregate predictor So that the actual predictor we would deploy at this point would be the sum of h1 plus h2. So, so this is an iterative learning process, or an iterative meta. This is an iterative meta learning process, where at each iteration of the meta learning algorithm, boosting, we get a new class of a regressor in this case, and then the final prediction is, in this case, the sum of all of them. And so we just repeat this process. So here's the aggregate predictor. And we get the residual of the aggregate predictor, which is this guy. We create a new training set of x comma y3. So those are the training set pairs. We train a new decision stump on x comma y3, which is splitting right here, and then we sum them up together again. So pictorially, since this is a one-dimensional regression, we can actually plot out what this looks like pictorially. So this is the y. This is the training set. It's one-dimensional regression. Y is actually x squared. This is the first decision stump that we train that splits on this feature. And this is our aggregate predictor, which is the same as their first only predictor, because the aggregation is just over one predictor. We create residual. So this is the residual of the aggregate predictor, y minus the aggregate predictor. We train a decision stump on this target, regression target. And we sum these two to get our new aggregate predictor, which looks like this. We again compute the residual of y minus the aggregate predictor, which is now the sum of these two guys. We train a new decision stump with this split. We sum those again, and so on and so forth. So this is, we can visualize what's happening in the one-dimensional case. But that's sort of basically what's happening. Each individual h is very simple. But as you sum over more and more, they start getting a little bit more sophisticated. So what I just showed you is what's called gradient boosting. A very simple version of gradient boosting, but nonetheless a gradient boosting. So here's sort of a little bit more formal way of thinking about it. We have a training set of XY pairs. Our initial aggregate, and we train as a low variance, high bias model on this training set. That's H1. Our aggregate model is just H1 because we've only done one loop of this meta learning algorithm. We create a new training set, which is x comma the residual, so y minus the aggregate prediction. That leads to another training process. We call our weak learner algorithm again on this training set. And our aggregate predictor is the sum of the two. And that is the process. Any questions on that so far? Okay, so before I explain further this idea of gradient boosting, let me take a step back to linear models and talk about axis-aligned gradient descent. So in axis-aligned gradient descent, we have a linear model class in this case with squared loss, and we're going to do gradient descent on this model class and loss function, but we're only allowed to make axis-aligned updates. So updates are of the form. This is of this form, where E sub D is the unit basis vector, which is 1 in the dth dimension and 0 everywhere else. And so what we're basically doing is we're projecting the gradient. So G is the normal gradient. We're basically projecting the gradient along the dth dimension, and we're just going to make an update in that direction. We get to choose the dimension. So and typically we choose the dimension that has the biggest projection. But that's the idea. So here's sort of a pictorial view. So if the minimizer, the loss function is here, and the yellow is the gradient, then the axis-aligned gradient updates are in orange. Okay, So that was in a linear space of models. Now let's talk about function space. So in linear models, a linear model is represented by one coefficient per feature or per dimension of my representation space. Ensemble methods give you one coefficient per model. So if I think of the space of all possible functions, so the space of all possible decision trees, and the axes of the space of possible decision trees are the space of simple decision trees. So let's say decision stumps. Then my ensemble is learning a linear combination over those. In the simplest case of the gradient boosting, the coefficients are either 1 or 0. It's 0 if I'm not including this decision stump. It's 1 if I am including this decision stump. Right. So there's some vast space of decision stumps out there in the world, or shallow decision trees, and I pick a few of them and I put a coefficient of 1 on those, and the rest are 0 by default. And that is sort of this is one way to think about ensemble methods. It's sort of a linear combination of over functions. And what we're doing is we're learning over the span of these linear functions. That's the function space. Okay, so in some ways, well, actually, in many ways, a function space is a generalization of a vector space. It has all the properties of vector algebra, and okay, so once we see this analogy between a vector space and a function space, and in vector space we do gradient descent. Well, how do we sort of do gradient descent in function space? In general, it's hard, but if we limit ourselves to axis-aligned gradient updates, then it becomes a bit easier. So every axis in this function space is a weak model. Of course, there's an infinite number of axes in this space, but we want to learn a linear combination of these weak models. Just if these in a linear model, each of these h's would be just a single feature, right? So in the degenerate case where each of these h's is just operating on only one of the features of a linear model class, then this actually exactly reduces to a linear model. Okay, so imagine that each of these axes is a weak model. Of course, I'm only depicting 2, but in general, it's an infinite number. But just imagine that. The goal then is to find, given a gradient update of what is the direction that minimizes the loss, find the single axis amongst an infinite number of axes that that projects closest to this this gradient. And so we actually do that by just a reduction to supervised learning, right? So we just basically say, okay, we need to project to the weak model that is closest to the gradient update that is hard to write down explicitly. So we're just going to reduce that to a supervised learning problem. It's the weak model that minimizes the residual squared error. That when I add that to my current function class, the joint function class is maximum reduction in squared error. It's the single axis upon which, when I move, I maximally reduce the squared error. Excuse me, if this was a linear model class with a finite number of axes, this would just basically be a for loop, right? You just run a for loop over all possible dimensions and see which one, gradient descent projected onto each of those, which one has the maximum reduction in error. In the case where there's an potentially infinite number, we would just replace this by some implicit optimization, or excuse me, by an optimization problem where we just assume we can solve this optimization problem. Right, so this is just the reduction back to vector space. If there's a finite number of these guys, and yeah. So axis-aligned gradient descent is in some sense equivalent to this, or analogous to this functional gradient. And you can think of it actually as a special case of a functional gradient. Okay. So in the full version of gradient boosting, we of course don't often have a step size here, Ada. I won't talk about how to set Ada in lecture. You can see this reference, but that's sort of the basic idea. So this is literally the full version of basic gradient boosting, which you see right here. Any questions on gradient boosting? Okay. So to recap, so you have an ensemble of many weak models. Doesn't have to be classifiers, actually. And the goal is to reduce the bias using only low variance. Using only low variance high bias models. We saw a derivation via gradient descending function space. And so that's what we've seen so far. And we've focused in these examples only in the regression case. What we'll see next is an example in the classification case. Yes?
So I'm wondering, are your weak classifiers generally going to be like decision stumps? So, like, do you have like one nonlinearity, more complex model?
Yeah, if you actually, if we just go back to so this is the aggregate predictor, right? If you keep doing this ad nauseum, it'll get back something that looks like the original function. Because each decision stump is splitting on a different feature, and it's a step function, basically. The decision stump is a step function splitting on a single feature, so that's actually inherently nonlinear. It's just a very simple nonlinear. It's a piecewise static function. A decision stump is a piecewise static function, which is inherently nonlinear, but is also very simple. And so many combinations of piecewise static functions can give you a very complex function. Okay, so next we're going to talk about AdaBoost, which is a boosting method for classification. Gradient boosting, it was designed for regression, right? Because you were literally regressing on the residual, which makes a lot of sense if you're trying to minimize squared loss. The residual is literally the update rule you want for minimizing squared error. You all derived this in homework 1. How do we do this for classification? And that's what AdaBoost is going to provide a solution for. AdaBoost is also an instance of functional gradient descent. Now, what we're doing is we are going to take the sign, of course, because we're doing classification. But otherwise, it's a sign of a linear combination of a bunch of weak models. So here's how we can combine multiple classifiers. Suppose each of these little h's is a classifier. And here are the weights. I should mention, these classifiers don't predict 0 or 1. They predict -1 or 1, just to make all the notations, just to make all the math and notations simpler. So sort of here's 4 data points, x1 through x4. Here's the predictions of these 4 simple classifiers. And f of x is the raw scoring function. That's a linear combination of these. And then h of x takes the sign. So at this point, I have not described the learning algorithm yet, just what does the ensemble look like. One thing that's interesting to note in these quote-unquote meta-learning or ensemble learning algorithms is that, by and large, I don't care what x is. Like I don't actually care what these x's actually are. I only care what these base models predict on these individual x's. Okay, so AdaBoost also creates new training sets, like in gradient boosting. In gradient boosting, the goal is to actually create a new regression target based on the residual, which is exactly what you'd expect if you're trying to minimize squared error. Okay. But AdaBoost needs to minimize a loss function that's, in some sense, corresponds to a classification error, which is a little bit different. The way AdaBoost goes about creating a new data set is it doesn't manipulate the labels of the original training set. It simply reweights the original training set. So let capital D define a weighting over the training examples such that the weighting sums to 1. So the default example is a uniform weighting, which weights every data point equally. We could have weight some data points none at all. This is an extreme example. It doesn't typically happen in practice, but we could say we don't care about one of the data points at all, and so on and so forth. And so now we have, when we learn a model with a weighted data set, we have a weighted loss function. Looks like this. So if all the D's were the same number, like a uniform, then this reduces to the standard supervised learning problem that we've been studying. But if the weighting is non-uniform, then we have to minimize this weighted loss function. And so just as an aside, training decision trees with weighted training data is not that hard. I'm just going to pick one of the impurity measures that we covered last lecture, Bernoulli variance, and all we require is just a slight modification of weighting each example. And then the size, the quote-unquote size of a training set, of a partition, is the sum of weights. So it's a really very straightforward modification of standard decision tree training. And this works for any impurity measure that's reasonable. Okay, so now we're ready to do AdaBoost. So in the beginning, we have our original training set, S, and the weighting is uniform, just like in the standard supervised learning setting. And we train a simple decision tree, a shallow decision tree, and we get H1. And I'm not going to tell you how to set the parameter alpha or A right now, but let's say we have it. And so this is the predictor. In the case where we only have a single model, the coefficient's irrelevant. It's just predicted to sign. Then what we do is we create, based on the errors that we make with this aggregate predictor, we reweight the data set. Intuitively, we'll weight difficult problems instances higher and weight easier instances lower. I'll make that more concrete in a few slides. And with this reweighting, we train a new classifier, H2. We pick a coefficient for it. We sum those two together, and this is our new aggregate predictor. Based on that, we reweight the data set again. Oops, minor formatting issue there. I'll fix that. And then we keep doing this until we decide to stop. And that's the basic idea of AdaBoost. And of course, I'll explain in detail what's going on, but this is the high-level overview of the algorithm. Okay. All right, so let's talk about some intuition. So suppose this was our aggregate scoring function. So this is our raw aggregate scoring function so far. And so for these 4 data points, if this was the true label, this is the aggregate score from the sum of these 4, and this is the aggregate classification prediction. Okay. So, okay, so let's say we get the first one correct, we get the second one correct, we get the third one wrong, and we get the fourth one correct. Furthermore, if we look at the raw score, the second row and the fourth row are very safely correct, right? We want the raw score for the third row to be positive, and it's a very positive number. We want the raw score of the fourth data point to be negative, and it's a very negative number. So in some sense, they're safe, right? If we add another predictor to this aggregate, even if it makes a mistake on 2 and 4, the aggregate will still probably predict it correctly. The first data point, the aggregate predictor is classifying it correctly, but the raw score is kind of close to the boundary of getting it wrong. And so there's a risk that if we add another predictor to this aggregate, and that predictor gets x1 wrong, we might make a mistake on x1 in the new aggregate predictor. The third example is just wrong. Like ideally, if we add another model to our aggregate, it should classify x3 correctly. In other words, what happens when we train a new model on F and it mispredicts on everything? So let's go through that experiment. So we're going to set the weight to 0.5 just for this example. And it mispredicts on everything. So it makes the wrong prediction on everything. This doesn't happen in practice, of course, but let's say that it's happening right now for this example. Then this is the worst case. This is the worst case for a coefficient of 0.5. This is the worst case aggregate predictor that we can get for these examples. Okay. Oops. Just plug this back in. Okay. So on example 1, it's kind of bad. We're getting closer to making a wrong prediction, but we're still making the right prediction. But if we do this again, we'll be making the wrong prediction. In example 2, it's irrelevant. We're still making the right prediction. We're still very far from the decision boundary. In example 4, it's irrelevant. We're still making the right prediction. We're still pretty far from the decision boundary. In example 3, it's very bad. Not only were we originally already making the wrong prediction, we're making it even worse. So when we train this new H5, H5 should definitely classify x3 correctly. It should probably classify x1 correctly, and we really don't care if it classifies x2 and x4 correctly or not. That's the intuition. And this is going to imply an algorithm that will reweight the data points for training x5. Any questions at this point? Okay. So the desired weight on these 4 training points should be medium, low, high, low, in other words, intuitively. Okay, so here is the AdaBoost algorithm. So we start with an initial weighting, which is uniform over all the training examples. We train the best simple classifier on this current weighting of the training examples. We compute the error, the weighted error of this classifier. And from that error, we determine a step size. This is the formula based on the error of this model. And then we update the weighting. So this weighting update is multiplicative and then renormalized. So we multiply the current weight by this term. So if h sub t disagrees with y, then this thing, so it's negative alpha or a times y times h of x, h sub t of x. So what this means is that if this current guy, if the current model that we trained, the simple model at the current iteration, gets it wrong, that means y times h of x is negative, then negative alpha times a negative number is a positive number. That means the weights goes up, because this a positive number is greater than 1. If the current base model that we just trained agrees with this label, then y times h is positive. So then the exponent here is going to be negative, which means e to this exponent is less than 1, so the weight goes down. And then we renormalize everything so that the sum of the weights equals 1. We'll talk about the specific choices of these formulas, but this does follow from the intuition slide that we had in the just before. Okay, let's go through an example. We have many training examples. I guess about 100. Here are the labels. Here we're just to show the first 4 data points, just to walk through the example. All the weights are uniform. Let's say we train a model. It has error 40%, and we set the alpha to be 0.2 according to this formula. And this is what it makes. This is the predictions it makes on the first 4 examples. It gets this guy right, so we downweight it. So instead of 0.01, it's now 0.008 according to this formula. We get this guy wrong, so we upweight it. Now it's 0.1012, so on and so forth. We train a new model. It has error 45% on this weighted data set. And the alpha is set to 0.1. And this is what it predicts on the first 4 data points. Again, it gets the first one correct. So it gets this guy gets downweighted even more. It gets the second guy correct. So it gets downweighted from 0.012 to 0.011. And so on and so forth. And this process continues. So if you only have about 100 data points in your training set, the numbers will look somewhat like these. So what happens if epsilon, the error rate, equals 0.5? So if epsilon equals 0.5, the numerator inside this log is 0.5. The denominator is 0.5. Therefore, the number inside this log of 1 is 0, alpha is 0. So this algorithm requires that your weak learner is slightly better than random guessing. Any questions on this example or the structure of AdaBoost? Yes?
Could you remind me what data you're training on when you go to the subsequent iteration?
You're training on the exact same data set. You're training on the exact same data set. So this is your original data set. And you are training on exactly this data set, just weighting the examples differently. So what that means is in normal learning, we would minimize a loss function. So this is the loss function of a single example. We would minimize just the sum of it, which corresponds to a uniform weighting. But here, we're going to weight some examples more and some examples less. And the reason that we do that, is because the goal here, the goal of AdaBoost is to add another a weak model to our aggregate model, and then look at the resulting aggregate classifier. So if the current aggregate classifier is safe on, let's say, example 2, because the aggregate is 3.1, the aggregate raw score is 3.1, which is very far from 0, then I can make a mistake. When I add a new model to this aggregate, I can make a mistake in example 2, and I'll still classify it correctly. So therefore, I could put a weight of 0 on it, and don't even care if I get it right or wrong, and still will be classified correctly in the next round. That's the idea. Any other questions? Yes?
You give some intuition that why when you're updating the L plus 1, you're also factoring in the DL and AI.
Okay, I need to parse your question. Hold on. Can you repeat that?
Sorry, so I don't really get why when you're updating B, you're also factoring in the previous B and previous A.
Ah, okay. So part of the answer will become evident in homework 3. But the basic idea is we don't want to make an update we don't want to make an update to the distribution that's a very big update from the previous distribution. So what do? We just make a small multiplicative rescaling of each data point relative to the previous weighting. Of course, we have to renormalize so it sums to 1, but yeah. And part of this is because this is like if you think about this as like a small gradient update algorithm, we're making small changes to the aggregate classifier, and so we also want to make small changes to the distribution over time. And so the step size alpha is both a step size for updating the aggregate classifier, also a step size in some sense for it's a multiplicative step size for updating the distribution weights. Okay, is that a question or no? Okay. Okay, so maybe this question will become a little bit, the question that was just asked will become a little bit more intuitive when we try to think about, okay, what kind of loss function is AdaBoost actually optimizing? And the loss function that AdaBoost is optimizing is exponential loss. This is a new loss function. And so exponential loss looks like this. So this is for classification only. So if y is your target, +1 or -1, then the exponential loss, and f is your raw score, the raw score of your model, not the sign of it, just the raw aggregate score. Then the exponential loss is e to the minus y times f of x. So it's this red curve right here. So if the target is a positive target, and you're super confident that it's a positive target, so f of x is a big positive number, then the exponential loss is very low. If you predict a big negative number, the exponential loss grows exponentially. Yes?
I think the previous slide, the AdaBoost Outline, only depended on the side.
slight notational mismatch. No, hold on. No, sorry. No. Okay, the connection is not clear, but F is the sum. F is the sum of, yes, F is the sum of all the alpha times little h's. Sorry, I should have made this connection more clear. F is, I define F, the raw score without taking the sign, as the sum of the little h's. And that's the same F I'm using here. It's the aggregate's raw score. So in this definition, I don't care where F comes from. It's just the aggregate raw score, or it's the raw score, aggregate or not. I could train a linear model with this loss function. It's just the aggregate score before I take the sign. In the with respect to AdaBoost, F is equal to the sum of the alpha times the little h's. I'm sorry, is minimizing what?
Is minimizing the exponential loss independent of what?
So this is just the definition of a loss function for classification. That doesn't really care what the function class is, as long as it has some raw score that you take the sign of. So this particular definition on this slide is agnostic to whether you're doing AdaBoost, a linear model that you take the sign of, or whatever. Of course, we're going to connect this F back to the aggregate raw score in the next couple of slides, but this particular definition is agnostic. Yes?
I'm not sure if I missed this, but on the previous slide, is there a reason for the choice of 1/2?
You mean this one? This 1/2? It comes from deriving. It comes from the. It comes. Well, it's a homework question, but it comes from proving that AdaBoost is functional gradient descent minimizing exponential loss. Okay, so let's decompose exponential loss when the raw score F is the sum of the alpha times the little h's. Okay? And so the first line is exactly just the definition. Now I'm going to invoke the definition of f of x equals the sum of alpha times h of x under the definition of the AdaBoost aggregate classifier. And so now it looks like this, the second line. So I've done nothing other than invoke the definition of f of x specifically for AdaBoost. And now I'm going to just use the exponential sum product of the exponent equality, identity, and rewrite it to look like this. So now the exponential loss looks like the product of the individual exponential losses for suffered by that particular base classifier. So we have little n base classifiers, and because exponential loss is the basically the it puts the raw score in the exponent, we can simply factorize it, and now the exponential loss is the product of the exponential loss of each base classifier times alpha, of course. By the way, this is also the distribution update rule. Remember when we were reweighting each data point based on how much Remember how we were reweighting each data point based on the performance of the most recently trained base classifier? And we wanted to basically do a small multiplicative update to each example. It's basically this. So we were reweighting each example by its change in exponential loss when we add this new base classifier to the aggregate model. Okay, yeah, so exponential loss operates in the exponent space. Therefore, an additive update to f of x corresponds to a multiplicative update of the exponential loss of f of x. And therefore, the reweighting scheme in AdaBoost can be derived via a notion of minimizing the residual exponential loss. So this is just the algorithm for AdaBoost again. And this, I just wanted here to highlight just the reweighting scheme. This is the reweighting scheme. And so if this base classifier reduced the exponential loss or increased the exponential loss, however much it reduced or increased the exponential loss, that's what changes in the weighting. Yes?
Instead of updating according to the sign, maybe if you just put the raw score there, that would be better, faster. That the multiplicative update,
If
rather than H sub B, you just put the raw to F sub B.
You could. There's nothing.
This doesn't treat points differently. That like if one was like correctly classified, but like is almost incorrectly classified, and there's one that's like correct or regular.
Right. Let me think about this.
So like that's why I asked how this can possibly minimize exponential loss of the raw score, because I don't think this like actually gets the raw score anymore. It just looks at the sign.
Let me see if I can understand your question. So the answer to your question comes from the fact that different base classifiers make mistakes on different examples. So if I keep making a mistake on this example, I'll keep boosting the raw score up by some increments. And also the weighting alpha also makes these numbers not the same, because each one has a different alpha.
So is the intuition like if you have 2 points that are both initially classified correctly, but one is like has a much larger raw score, then in subsequent like simple models,
It'll get weighted even lower, yeah.
more likely to fail the closer.
Yeah, so the idea is, so perhaps your question comes from, it's easier to understand the essence of your question if we only look at the first iteration of AdaBoost, where the model, because it's the base model is a classifier, not the raw score of the base model, it only predicts +1 or -1. So if it gets 2 examples correct, we downweight by the same amount. If it gets 2 examples wrong, we upweight by the same amount. And your question is, well, okay, even within the base model, we don't know its internal confidence, which is essentially what you're asking. And so, A, does that hamper AdaBoost in the sense that AdaBoost can't converge to something good? And B, can we do better if we looked at the raw score instead of the classification process? To answer question A, it does not prevent AdaBoost from finding a good model because because the different classifiers make mistakes in different examples. So the answer to your first question, AdaBoost will still converge, as long as you can keep finding a classifier that's better than random. To answer your second question, I actually don't know the answer to that. Whether or not if you use the underlying raw score of h of x of the basis classifier, whether that would speed up AdaBoost. I believe the answer is I believe the answer comes from the fact that you want each of these h's to be bounded in order to guarantee convergence. So when you study the convergence of like stochastic gradient descent, or even when I showed the analysis of perceptron, the analysis of perceptron, the convergence rate dependent on the radius of the input space, if you recall. The mistake bound of perceptron depends on the radius of the input space. The same is true in stochastic gradient descent. The rate of convergence depends on the radius of the feature space. So in AdaBoost, you could think of the radius as the maximum value that one of your base functions can output. So you need that to be bounded to prove convergence. It doesn't need to be between -1 and +1, but for simplicity, they just did that. I'm not 100% sure if that's true for AdaBoost. I know it's true for everything else I just said. I'm 99% sure it's true for AdaBoost. That you need because it's true in all other optimization problems, that whatever you're optimizing over, the weight of the things that you're putting coefficients on have to have a bounded domain. Okay, so the way you prove that, so I just gave you I gave you the connection that AdaBoost appears to be minimizing exponential loss. And the derivation, once you sort of understand the structure of it, and we're going to walk you through the structure of it, is relatively straightforward. And it's a nice exercise if you're interested in sort of this line of thinking in machine learning. So how do you, design these algorithms that provably do something with respect to a loss function? And so there's basically 3 steps. First, you prove the exponential loss, upper bound 0,1 loss. Pretty obvious. Second, you relate exponential loss to the normalizing coefficient. That one's not that hard. And then finally, you justify your choice of alpha. And you do that by setting some gradients and taking it to 0 and noticing that this is the best step size that you can do. So once you have the framework for this kind of analysis, the analysis is pretty straightforward. Of course, this is a classical result. Please don't look on the internet for the solution. We walk you through it, and it's a nice exercise to put yourself in this mindset. And if you're interested, if you find this kind of homework question really interesting, then you may find sort of this type of theory in machine learning interesting as well. So just to recap AdaBoost, it's gradient descending function space, the space of weak classifiers. The final model is a linear combination of weak classifiers. And the way we think about doing it is we create these new training sets. Unlike gradient boosting, where we change the regression target, in AdaBoost, we simply reweight the data points. And this comes from deriving what is the correct thing to do for minimizing residual exponential loss. Changing the regression target to the residual is the quote-unquote correct thing to do if you want to minimize the residual squared loss. Reweighting turns out to be the right thing to do if you want to minimize the residual exponential loss. Any questions before I move on? Okay, so now on to the last bit of the lecture, ensemble selection. So we've spent the bulk of this lecture and the previous lecture obsessed over the bias variance decomposition. And in fact, the bias variance decomposition is one of the fundamental concepts in machine learning. I always present it for squared error because it's mathematically clean. It gets very ugly for other loss functions. But it is one of the fundamental concepts in machine learning. And people look at it over and over again in various contexts. But, you know, we don't go through this careful analysis of, you know, oh, let's take high variance, low bias models and reduce the variance by just averaging a bunch of high variance models. That's what bagging is. Or we look at, you know, high bias, low variance models that are very stable, so we don't really care about overfitting for these high bias, low variance models, and we just find interesting ways of combining them so that the resulting model is complicated. But, you know, is there any way that we can get the best of both worlds, or, you know, almost the best of both worlds? And so the insight is, well, let's just use the validation set, right? This is sort of the default answer of any applied machine learning person. Anyone who uses machine learning in the wild, at the end of the day, because the theory, although it's very interesting, and I'm personally very interested in the theory, there's a gap between theory and practice, what the theory can rigorously tell you and what you can do in practice. And so while the theory can guide a lot of the algorithmic decision making for designing an algorithm, these algorithms often come with a few parameters, hyperparameters, assigned decisions that the theory doesn't tell you enough about. And so what do people do? They use a validation set. This is the default answer for anyone who uses machine learning in the wild. Use a validation set, whether it be cross-validation or just one splitting of the training into a training and validation. Either way, you know, use a validation set. And so what does the validation set give you? Well, we have this error over the validation set. And the reason why we use a validation set is because it's a held-out data set that we don't train on. And so it hasn't been tainted with our training algorithm. We haven't looked at it. So we can use it as a proxy for test error. So, okay, the reason why we went through all this, all these exercises for bagging and boosting is because we ultimately wanted to minimize the test error. The bias variance decomposition that I gave you is a decomposition over the test error. And by looking at that bias decomposition, we could come up with bagging and boosting and all these things. But suppose we just sort of trusted the validation set. If the validation set is a good enough proxy for test error, what would we get? What would be the algorithm that we get? And one algorithm is called ensemble selection. So we have our original training set. We do the standard splitting it into a sub-training set that we use for training and a validation set. And just for simplicity, let's say we have a set of models that we train on S prime. You know, random forests, neural nets, decision trees, even bagging and boosting, whatever. And now, what ensemble selection does is it maintains an ensemble as a combination of the models that we've trained. So it's like this. And every time we add a new model to this ensemble, we simply add one that maximizes the performance on the validation set. So, you know, in practice, what that means is we run a for loop over all these models, try adding one to this ensemble, and then look at the resulting performance on the validation set, and then commit to the one that maximally improves the performance on the validation set. And then we repeat until we decide we're done. So, in other words, our base models are trained on S prime, but the ensemble is built to optimize V prime. Okay, so recall that the expected test error is, a bias plus variance. Bagging, we come to low bias models and we try to reduce the variance. boosting, we commit to low variance models and we try to reduce the bias. Ensemble selection basically says, well, you know, math is cool, but you know, why don't we just do what people actually do in practice, which is minimize error on the validation set, because ultimately that is, in many cases, the best proxy we have for test error. Right, so we use validation error to approximate test error. We don't care what the bias variance decomposition is, because caring about the bias variance decomposition in these ways is just a way of getting to minimizing test error. And if we can just directly use the validation set as a proxy to test error, we don't care what the bias variance decomposition is. So what's the catch? There is a catch, like everything. The catch is that ensemble selection heavily relies on the reliability of your validation set, not surprisingly. And this isn't always possible. And so if your validation set needs to be big enough to be reliable, that means that you have less data for your training sets for training your base models, which means your base models can be worse than the base models that you're working with for bagging and boosting. Whether or not that makes a difference in final overall performance, it depends. Yes.
Why don't we worry about now that we're overfitting on the validation?
Great question. In ensemble selection, are we worried that we're overfitting to the validation set? The answer is yes. If you overuse the validation set, then you are potentially overfitting to it. The good news is that the way we use the validation set is not as bad. So what does that mean? In statistics, there's a notion of concept known as multiple hypothesis testing. And so when you train a model on a data set, then let's say this data set is d-dimensional, then the probability of overfitting, or the risk of overfitting increases with the dimensionality of the data set. And that has a direct correspondence to concepts like multiple hypothesis testing. You're reusing the data set over and over again because you're trying to estimate coefficients in a linear model of d coefficients. In the validation set, we don't care about the features. We only care about one number, which is the overall performance. So instead of trying to estimate d numbers, which is the linear model, we're only trying to estimate one number. And so from that perspective, intuitively, it takes more. We have to query the validation set more to overfit to it than the training set. Roughly, at least compared to linear models, by a factor of d. But it is a concern. The kind of meta, the next level approach would be to have another validation set. Right, you split your data into training, validation set for ensemble selection, and then validation set for early stopping. So you have two validation sets, and you only use the last validation set for early stopping when it starts going down. Most people don't do that because you're not querying the validation set enough to overfit to it too badly in most cases. Yes.
Do you do any weighting of your hypotheses as well? Or
in the classical ensemble selection method, there was no weighting. You could, of course, weight, but what typically happened is you just added in increments of 1. So H1 and H2 could be the same base model, for example. Well, okay, that's never going to happen for H1 and H2, but H1 and Hn, right, could be the same model. Yes?
So here you're saying you maximize performance of H on the front, you add the model that maximizes the performance of the aggregate? Or
Yeah, sorry. So, sorry, this is a slightly ambiguous language. add a model from H to the aggregate such that the aggregate maximizes performance on V prime.
So then, how come the models themselves are trained as like standalone, but then you're testing it as like part of the aggregate?
So this is also a form of functional. Well, this is a form of functional gradient descent, or and this is so I predefine my function space.
Like it's trained on the same set S prime, right? There's not like a residual set that each of them.
That's right. So okay, I see what you're point. So in boosting, so maybe this connection will be in boosting. Assume that my set capital H, that corresponds to ensemble selection, if I were to use the same notation, is the set of all possible shallow decision trees. So it's infinitely many. And this training algorithm in the first line of this for loop is just a method of selecting one of these infinitely many shallow decision trees from which I build it up. There's a version of boosting where I have a finite number of decision trees. I've pre-trained all the decision trees that I cared about. In which case, the first line is literally just a for loop over my finitely many trained decision trees, and I pick the one that minimizes the residual exponential error. And that's what's happening here. I'm running a for loop that minimizes my residual error on the validation set. So I run a for loop over my finite number of hypotheses, base models, and I add the one that minimizes the residual error on my validation set. In bagging and boosting, especially boosting, there's the way that they set up the algorithm. You can assume an infinitely sized capital H, the space of all possible shallow decision trees. But actually, nothing changes in the boosting algorithm if the space of all possible models you're allowed to add is finite, and you just run a for loop. Nothing changes. Yes?
Why isn't there a 1 over n or something as sum of ensemble members?
I don't know that would help much.
What are we doing with H? Is it for classification? We're just taking the sign? Is that
So they left it at this generic state. If for classification, H could be the sign, could be the raw score, and then you take the sign afterwards. So I left it fairly generic here. You could customize it to classification or regression, and for regression, it's just you just sum it up. Yeah. Any other questions? Okay, so here's just one example of ensemble selection in practice. This is an average over multiple data sets using multiple error metrics. And ensemble selection was the best performing method, outperforming many other methods. Wins a lot of competitions. And ensemble methods, maybe not ensemble selection, but ensemble methods these days are still used. If you want the best possible performance these days, you train an ensemble of deep neural nets, and you average their predictions. Most people don't do that because that's a very expensive operation to do. But if you care about accuracy more than anything else, then that's what you would do. further reading on ensemble methods. And next week, we'll start with deep learning. It'll be taught by my PhD student, Joe Marino. And next Thursday, there's a recitation on Keras, which is the deep learning Python package you'll be using for the homework for next week.